Welcome to this talk on an experience with code size optimization for production iOS mobile applications. I am Milind Chabbi. I am a researcher in the programming systems group at Uber. This work is done in collaboration with my colleagues Milind and Barik. Uber is a mobile first company. Uber Rider, Uber Driver, and Uber Eats are some of our flagship mobile applications. Riders use Uber Rider app to order cabs. Partner drivers use Uber Driver app to pick up, navigate, and interact with the rider. Eaters use Uber Eater app to order food, groceries, and a growing list of other things. There are iOS and Android versions of these apps. iOS is the matter of discussion in this talk. Our iOS mobile apps are large in size. The over-the-air download size as of today are 157 MB for Uber Rider, 115 MB for Uber Driver, and 122 MB for Uber Eats, and they are growing fast. For the rest of this talk, I will focus on Uber Rider, but the findings generalize to other apps as well. The Apple App Store has limitations on over-the-air app download size. Apps exceeding this limit cannot be downloaded over the air, but only over a Wi-Fi connection. The size limitations have been 100 MB in 2017, 150 MB in 2019, and 200 MB in 2020. Crossing this download size means the first-time users cannot download the app over the air when they need it most, and we cannot deliver new features or security updates. This limitation can result in revenue loss. In a limited study for the Uber Rider app, we found that crossing the download size limit results in about 10% reduction in app downloads, 12% reduction in signups, and 20% reduction in first-time ride booking. The Uber Rider app has inched closer to the download size limits several times in the past 3 years. Others have independently concluded that one of the most crucial pain points, especially in building an enterprise mobile application, is to constrain the app size well below the size limit. Hence, we set out to reduce Uber iOS app size with the following objectives. First, bring the size to be well under the app size download limit. Second, choose an optimization that continuously delivers impact for the foreseeable future as the app evolves. Third, be transparent to application developers. Fourth, do not regress the performance of critical use cases. And fifth, do not increase the local build times. Here are some of the salient features of the Uber Rider app. It is written in a mix of Swift and Objective-C, predominantly Swift. It is about 2 million lines of code. Swift is our programming language choice because of its reliability and productivity features, strong static typing, extensive error handling constructs, and automatic memory management via reference counting. These features, although useful, come to hurt us in app size as it becomes evident soon. The app consists of over 450 Swift modules, out of which more than 60 are third-party modules. The app has a very fast development and release cycle with weekly releases. Numerous features and experiments are always added. The software is layered, templated, and has pluggable modules. The components are designed for testing and mocking. The app itself is statically linked. We typically produce a 64-bit ARM binary. 92% of the app is the binary. 77% of the binary is the machine instructions. Since machine instructions form the vast majority of the app, it is the focus of our size optimization. A typical iOS app build workflow looks like this. All Swift files belonging to the same module are compiled together using the Swift-C compiler into an object file. If you use Objective-C, they are compiled via the Clang compiler. All object files, each representing an independent module, are linked with the system linker to produce the app binary. The final app itself may contain other resources such as media. For each module, we apply the size and whole module optimization flags to reduce the app size. However, in this default workflow, one cannot do any inter-module or link time optimization. In fact, LTO was not possible in mixed language apps prior to our work. Size optimizations are pervasive in the compiler literature. Before diving deeper into our work, I would like to allude to a few options we explored. We explored identifying function level similarities at AST and found less than 1% duplicates. We explored SwiftIR, also called as SIL, and the impact of its outlining optimization, which uses function calls instead of inline sequence of instructions for common operations such as object copies. It delivered only about 0.4% size reduction. LLVM offers several size optimizations. The merge function pass retains only one instance of function bodies that are identical. This offered us about 0.9% size reduction. The FMSA sequence alignment pass delivered about 2% size reduction on our app. A very recent merge similar function pass was not suitable candidate due to its very large compile time. An emerging IR outliner in LLVM is not target aware. In contrast, finding machine code sequences that repeat and replacing them with a single instance, which is the topic here, gained us about 23% size savings. We extensively explored the machine code of our app, trying to understand the nature of replication of machine code. We were after replicas because if we find a lot of replicas, we can do something about them. This is fundamentally a whole program binary analysis. We match straight line sequences that are identical in the binary. We maintain a mapping of repetitions back to their source code for further analysis. The matches need not be of sequences of identical length. A substring match suffices. A subsequence is not a match. We use a suffix tree to hold the substring matches. A basic block is the largest granularity of a match. We do not go beyond a basic block because it is not straightforward to remove replicas involving control structures. This figure summarizes the pattern of repeats we found in our app. In this picture, each point on the x-axis represents a unique machine code sequence. They are ordered high to low by how frequently they appear. For example, the sequence that repeats most frequently has an ID 1 and appears on the leftmost point on the x-axis. The next frequently appearing sequence has an ID 2 and appears next, and so on. The y-axis on the left side shows the frequency of repetition. The blue line plots the frequency of repeats of each sequence. It is worth noting that the light blue line overlaid on top of it shows a perfect fit to the power law equation. Also present in this figure is the red line, which plots the length of each sequence, which is shown on the right side of the y-axis. All axes are in the log scale. We make the following observations. Repetitions of machine code sequences are highly common, and over 100K unique sequences repeat in the app. This is not counting how many times each sequence repeats. The frequency of repeats follows the power law curve, and it has a very long tail. Sequences that have a high repeat frequency have a short sequence length. Conversely, sequences that have a long sequence length have a low repeat frequency. In this slide, We plot the same figure with the x-axis in the non-log scale. Focus on the red line. All points between two spikes represent a cluster of sequences that all repeat for the same number of times. However, we notice that as the repeat frequency is lower, the width of the clusters grow. That is, we find more variety of repeating patterns. Within a single cluster, where each sequence repeats same number of times, we notice that the patterns that are longer are very few, whereas those that are shorter have many varieties represented by the length of the horizontal steps. Thus, the whole graph unfolds like a fractal where we see a recursive repeat of the same findings. We exploit this nature in our optimization later. Here are a few most frequently repeating patterns. This two instruction sequence moves a value in register 20 into register x0 and calls swift release, which decrements a reference count of the object in x0. It repeats 46,000 times. This is a similar sequence as the previous one, with the only difference that the object in this case was present originally in register x19. Similarly, here is a sequence that calls swift retain to increment the reference count of an object, and this sequence appears 24,000 times. Similar release and retains happen on Objective C code also. We can observe that a lot of sequences repeat due to reference counting language feature and the necessity to adhere to the calling convention. Many patterns exist because of the register choice, the callee function, or even the callee signature and the associated instruction ordering. Yet another cause of repeats is due to the Swift generics, which results in repeated machine code sequences for different instantiations. Since we extensively use generics for code maintenance, it leads to a large binary footprint. Swift also provides closures and performs closure specialization, which results in repeated code fragments at different specialization points. An interesting repetition happens due to the extensive use of Swift's try expression. We often use try expressions to read fields from serialized JSON objects as shown here. In fact, this is the recommended way to deserialize. Large JSON blobs result in a long sequence of try statements and object field assignments. These try expressions create many error handling basic blocks, each with similar code. The out of SSA transformation causes long sequences of copy statements in each predecessors of a fee block. Such low-level causes of code bloat are visible only via our binary analysis. So, what is the solution? I have already alluded to the solution, which is to outline repeated machine code sequences with a control transfer to a single instance, like a function call. Let's see how this works. Here is a sequence of two instructions that I showed previously. The first instruction moves the register x20 to register x0, and the second instruction makes a function call to Swift release function. Assume this sequence appears 1 million times. That is, 1 million times 2 instructions times 4 bytes per instruction is 8 megabytes here. Let's substitute each of these two instruction instances with a single instruction that diverts the execution to a special stub. Let's call the stub as the outline function. The stub now performs the movement of x20 to x0 and then branches to the same target function, Swift release. The execution of this sequence accomplishes the same semantics as the original one. This version, however, has 1 million times 1 instruction times 4 bytes per instruction plus 2 instructions of the stub, which is about 4 megabytes in size, a 50% reduction in size. LLVM's machine outliner pass performs exactly this transformation. It substitutes repeated occurrences of sequences with a branch or a call to a single instance. In doing so, it also analyzes the cost and benefit of transformation and performs the transformation only if it is beneficial to reduce the size. The order of selecting the candidate sequences is a knapsack optimization problem, which is NP hard. LLVM implementation employs a greedy heuristic. I previously mentioned that the iOS build pipeline performs only intra-module optimization but no inter-module optimization. This module-level optimization squanders the outlining opportunity. In an app with 500 modules, the outlining would leave 500 replicas of outlined functions, one each in every module. It will also miss the replicas that may be found between modules. We address this limitation in our iOS build pipeline by compiling each Swift and Objective-C module into LLVM IR while doing all Swift level optimizations for each module. We then merge all LLVM IRs into a single IR using LLVM link. We then apply LLVM IR optimizations as usual but on the whole module. We then lower the LLVM IR to machine code, and in this phase we apply machine outlining on the entire binary. Earlier I mentioned that we cannot merge mixed module LLVM IR files. We fixed that in the LLVM link and clang so that we can now merge them. Earlier I mentioned that LLVM's default outliner employs a greedy heuristic. Here is an example with 8 sequences, of which 5 are ABCDs and 3 are BCDs. Since the suffix BCD appears 8 times, the machine outliner's greedy algorithm picks BCD and adds a single instance and branches to it, which results in the total size of 16 instructions. However, it stops at this. We can see that once the optimization is done, it creates new replica sequences such as AX here. We developed repeated machine outlining, which performs machine outlining recursively on these candidates. In this case, it adds another outline function with sequence AX, where X branches to the already outlined BCD sequence. We don't stop here. We repeatedly perform this optimization and exploit the fractal nature of folded outlined instructions to squeeze more size. I made all of this look easier. There are several implementation subtleties. We address the upstream compilers and LLVM link to merge metadata in LLVM IR produced by different compilers. We maintain register liveness information across recursive outlining repeats. Finally, we also had to perform a careful data layout optimization when linking modules to retain the relative order in which global data appears in constituent modules. This was necessary to ensure good runtime performance. I will now show some of the evaluation of this optimization. First, I show the size benefits. In this figure, the x-axis shows the number of repeats of machine code outlining. The y-axis shows the size in MB. The top 2 lines show the size of the app binary, and the bottom 2 lines shows the size of the code section. The blue line is the size with intra-module optimization only, whereas the orange line is with our inter-module optimization. Similarly, the red line is the size with intra-module optimization only, whereas the black line is with our inter-module optimization. Inter-module, 5 runs of machine code outlining delivers a 18% binary size reduction and a 23% code section size reduction. Inter-module outlining clearly wins over intra-module outlining. It produces a 12% smaller code. Repeated outlining by 5 times contributes to 27% of the total code section size savings. We tracked the benefits of our optimization on the Uber rider app for close to an year and noticed that it not only reduces size, but the percentage reduction grows with time. We see that our optimizations reduce the code size growth by 2 times. Hence, the optimization has a long-term benefit. Outlining can hurt performance when done in hot loops. To evaluate performance impact, we selected a handful of critical code parts chosen by the app developers as sensitive to performance. We measured their running time before and after our optimizations. We collected the data from millions of users using a variety of different hardware and software configurations. In this graph, we are plotting the ratio of execution time with our optimizations divided by the execution time without our optimizations. Hence, lower is better. Bluish color indicates that our optimizations had a positive effect on the running time, and the reddish color indicates that it had a negative effect. In almost all cases, we had either no effect or a positive effect with minimal red cells. On average, from millions of data points, we observed a 3% performance improvement as a result of our optimizations. Our optimizations introduced an extra 45 minutes to the build time. Since we did not want to impact our developer local build times, we excluded this optimization from developer debugging builds, but only enabled it for testing and release builds. In summary, we set out with these objectives and accomplished them all. We brought the size well under the App Store download limit. Our optimizations show growing benefits over time. Our optimizations did not require developer involvement. We did not significantly regress app performance. We did not increase the local build time. To conclude, observing repeated machine code at the binary level offers new avenues to reduce code size. Repeated machine outlining with intermodule optimization reduces app size. We were able to reduce the Uber rider code size by 23%. We also applied it to Uber driver and Eats and reduced their sizes by 17 and 19% respectively. Our optimizations are in production since 2019 and being used by millions of daily users. Machine outlining has no performance impact when done on UI-heavy applications. The worst case slowdown was only 10% for a synthetically created loop-bound benchmark. There is scope to explore more. Our findings generalize to other codes such as the Linux kernel and the Clang compiler. We can expand the outlining to semantically equivalent code sequences. We can explore code generation that favors more outlining candidate. This concludes my presentation. Thanks for attending.